friends, welcome to Emmanuel Tutorials. Today we'll be learning about a tree known as a binary search tree. As the name suggests, the tree is a binary tree, which means the maximum number of children that each node can have is 2. That is, each node can have either 0, 1 or 2 children, and the word search indicates that it simplifies the process of searching an element in the tree. Now, we'll see how it works. The reason why it simplifies the process of searching is because for every node present in my binary search tree, the left element, that is the left child of the node, is lesser than itself and the right child is greater than the node. For example, if I have a node 44, 22 and 66, this is a binary search tree because considering 44 to be the root of the tree or simply any node of the binary search tree, the node present to the left of the node of element 44, that is the left child of 44, is lesser than 44 and its right child is greater than 44. And this is the most significant property of a binary search tree, which reduces the searching time, that is the time complexity, to big O of log n. Whereas for linear search, the time complexity required is big O of n. So if I have to insert some elements into my tree, 27, 35, 12, 17, 63 and 44, I have simply taken any random elements. The insertion would be the first element that I have would always be the root of my tree. So 27 has become the root. Next, I have to insert 35. Now we compare. 35 is not lesser than 27. Instead, it is greater than 27. So it would come to the right of 27. So I have finished inserting 35 into the tree. Next, we look at 12. 12, we compare first of all to the root. Since 12 is lesser than the root and there is no element present to the left of the root, we would insert it to the left. So I have finished inserting 12 as well. Now I wish to insert 17. As I said, we always start comparing from the root. So we compare 17 with 27. It is lesser than 27, so we move forward. But we see that 17 cannot be accommodated here because there is already an element. So we compare 17 with that element over here. That is, we compare 17 with 12. We see that 17 is greater than 12. So we insert it to the right of 12. So I finished inserting 17 as well. Now I wish to insert 63. I'll start comparing from the root. 63 is greater than 27. So move to the right. Again 63 is greater than 35, so move to the right. Since I have found a vacant position in the tree, I will insert it there. So I finished inserting 63 and the last element to be inserted is 44. Again I will start comparing it from the root. 44 is greater than 27. Since it is greater, I move to the right. Again I see 44 is greater than 35. Again I move to the right. And then I compare 44 with 63. 44 is lesser than 63 and I see that there is a vacant position to the left of 63 and so I would insert it there. And this is the resultant binary search tree with time complexity of the best and average case as big O of log n. So if I wish to search an element 44, I do not have to compare the element to be searched with each and every node of the tree. I simply have to start from the root. I will check whether 44 is lesser than 27 or greater than 27. Since I have found that it is greater than 27, I will move to the right. Again, I will compare 44 with 35. Since it is greater, I will move to the right. And then I will compare 44 with 63. Since it is lesser, I will move to the left and the element is found here. This is the advantage of a binary search tree because at the most I only have to traverse half the tree. I have not compared my element to be searched with any node in the left subtree, which makes it a simplified process in searching. However, a binary search tree does have some limitations when it is a left skewed or a right skewed tree. For example, if I have been given some tree as 1, 2, 3 and 4, this we find that it is a binary search tree because all the elements to the right of each node are greater than itself. That is, 2 is greater than 1, 3 is greater than 2 and 4 is greater than 3. And also that all the elements present to the right subtree of 1 are all greater than the root of the tree, that is 1. And so it is a binary search tree. And here if I wish to search element 4, I have to traverse the entire tree because first I'll compare 4 with 1, it is greater, so I'll move to the right. Again I'll compare 4 with 2, since it's greater, I'll move to the right. Again I'll compare 4 with 3, and since it's greater, I'll move to the right and the element is found. However, we find that I have traversed or visited every node of the tree, and this does not reduce my time complexity in any way, and it results in a worst time complexity of big O of n, where n is the size of the input. That is, here since I have 4 nodes, I have traversed all the 4 nodes, which gives it a time complexity of big O of n. So to overcome this limitation of a binary search tree, we have another tree known as an AVL tree, which has some unique properties and maintains the time complexity to big O of log n. We'll be looking at the AVL tree in the upcoming videos. Thank you for watching. Please like, share and subscribe our channel, and also check out our other videos. Thank you.